All right, so we're moving along with properties of liquids. My third is I want to talk about water in more specific specificity, I guess you could say, more specifics to water. And there are some actual unique properties to water. And for example, the solid is less dense than the liquid. Water, when it freezes, is less dense. Whether or not you know that if you take some water, okay, there's some liquid water, okay, and you freeze it so that it is a solid, it will expand. If this was ice now, it expands. If you fill up a water bottle completely to the top, put it in your freezer, it may explode. It may crack the bottle as it freezes because it expands. Okay? The reason that is because water molecules, when they're in the liquid state, although they have intermolecular forces, okay, they're pretty much all randomly located. They're kind of all over there, holding them pretty tight, very strong intermolecular forces because it is hydrogen bonding, but they're random. When they form solids, so this would be in like the liquid state, okay, when they form solids, and again I'm talking about water in this case, they become very arranged, I guess I could say, in this real patterns. Okay, so here's 4 water molecules, and what that does, let's get a is it creates gaps. And again, let's say that would be, you know, it'd be kind of all over the place. It creates little gaps and holes and spaces. Okay? And those spaces allow it to be less dense. There's less spaces, so it expands. Why does it expand? Because they get further apart, which is less dense. That's why ice floats on top of water. All right, we'll talk about it more in our class, but that's the basic idea of the density of water. All right, it has a high viscosity and high surface tension compared to what we would think it is. It's just a very small molecule. 1 oxygen and 2 hydrogens, but it has a higher viscosity and surface tension, and that's due to the intermolecular forces being higher, hydrogen bonds. It has a higher boiling and melting points, again, than we would think it would. Most molecules that are very small, H2O, don't have a lot of substances, a lot of atoms making it up, and certainly H2O, we would think that it would have a lower boiling point, melting point, maybe a gas at room temperature, but because it has hydrogen bonding, then it is it's higher than we would think. It also water absorbs large amounts of energy without big changes in temperature, and that's due to the high heat capacity. All right, so specific heat of water, 4.18 joules per gram degree Celsius. You can put a lot of temperature, a lot of heat on water, the sun for that matter, and it doesn't change the temperature very much. Obviously, if you see here, if you've got a swimming pool, okay, this is all water, and right next to it you've got a deck, a wood deck, or a cement block or something. You walk around in the summertime, it's going to be very, very hot on those feet, as opposed to if you jump into the pool, here's your picture, you're much happier because it's a lot cooler, because the water, even though the same sun is beating down on the deck and on the water doesn't absorb as much energy, or it absorbs the same amount of energy, but it doesn't change its temperature as much. And that's a good thing. We can jump in some water. Okay? And the last thing I'll mention about water is that it's a universal solvent. Okay? Moving along. I want to quickly talk about evaporation. Evaporation is when a liquid converts to a gas when not boiling. So if you have a cup of water, there are molecules at the surface. Without putting a temperature, putting some flame underneath it, right? If we boiled it, we could basically add energy to the molecules. It causes the intermolecular forces to be broken, and then the molecules can go into the gaseous state. So if I remove that heat, these molecules they're still moving. So they're in the liquid, they're still moving. They're trying to get away, and if they can finally get away, that's evaporation. Okay, some substances evaporate quicker than others. If you said you had something with a high surface tension, this is A, let's say, versus something with a low surface tension, we could talk about viscosity as well. Which one would evaporate easier? Well, the one with the lower surface tension would evaporate easier. If I put these on a desk again, this would evaporate much easier because there's weaker intermolecular forces here. So weak intermolecular forces. So therefore the molecules would be able to move away from each other a lot easier, as opposed to something with a high surface tension. So that's the evaporation. And the last thing I want to quickly mention about properties of some liquids is vapor pressure. Vapor pressure is a measure of force exerted above a liquid. It kind of goes in with evaporation. In closed systems, I'll let that typing, and I apologize for the typing. In a closed system, so again, if we had a container that had some liquid in it and it was closed, all right, then the vapor pressure is equal to the evaporating and the condensing particles. So evaporation, condensing, that's why if you have a container that's closed, then liquids will stay in solution. They'll stay as a liquid. If this same container was not open, then these molecules would evaporate. Obviously, if you increase the temperature, then your vapor pressure could change as well. It's the measure of force exerted above a liquid. All right? The next thing I'm going to talk about, and that's going to be on the next slide, is boiling points, and we'll take a look at it then.